So our final topic for this unit, again, conservation of energy as well as power. So for this one we have the same roller coaster we saw last day. And we're just going to make sure we understand the difference between total energy, potential energy, and kinetic energy. Because the whole idea is that if energy is conserved, the total energy at each point is going to remain constant. So what we can see, it's easier to think of as the bottom as our reference line. So I'm going to say that's our zero height. Right, that bottom line, zero height. So our total energy, so at A, assuming where the car is starting at rest, which it says in the question at rest, initially there's no kinetic energy, so it has only potential energy. That means our total energy is, so when we add up the potential and kinetic energy, our total energy is equal to our potential energy. If B is where we are considered to have zero potential energy, at that point, our total energy should still be the same, but all that potential energy is converted to kinetic energy. So the energy is conserved, just PE has become KE. At that point, somewhere in the middle, total energy is still the same. So we haven't lost any energy. In real life, as the car is going over, we hear all that sound, there's that friction, there's sparks flying. That is all examples of energy loss. But we're assuming conservation right now. So there, our potential energy is not quite halfway, so maybe around there, just doing approximation. And our kinetic energy is going to be right up there. But if I were to add those together, this needs to add up to my total energy. So we scroll down to our first question. So it says that assuming the height of A in the previous example is 14 meters, calculate the velocity of the car at the bottom of the hill B, assuming the initial velocity was 0. So energy, so basically what's happening in this one is energy at A must equal to our energy at B. So we have potential energy at A plus kinetic energy at A is equal to our potential energy at B plus our kinetic energy at B. So if it's at A, initially the kinetic energy is 0, so that goes away. At B, our potential energy is 0, so that just simplifies down. So you see you get mgh is equal to 1/2 mv squared. The potential energy at A must equal to the kinetic energy at B. You can simplify it down because they both have a mass term that is equal to each other. And we can see that we can solve for velocity. It's just the square root of 2 multiplied by gravity times the height. Plug it in, we get 28 meters per second. For question B, this is the height of the car when it's traveling at half its max speed. So we know that the energy at any point in the ride is the same. So we want to find out when PE, and so we're going to have potential energy and kinetic energy. So I can choose any point. So I could choose that mgh at A again. Just that, so it'll give me how much energy I initially have. And later on, we're trying to find out how high are we. So mgh when we're at that halfway point. Sorry, that's not what I want. We want trying to solve for height when our kinetic energy is half. Okay, so plus 1/2 mv squared where our speed is half. Just found our maximum speed is 28 meters per second. So you see the masses are going to cancel out. We have g times 40 meters. That will give us our total energy. Solving for the height when our velocity is half our max, which is 14 meters per second. Plugged all in, we end up with h is equal to 30 meters. So because it's a v squared relationship, it's not just going to be half speed is half height. We have to take into account that square. So we get 30 meters as our height.